So now at point B, now, the object has been made to move, isn't it? It has been made to move from this point to this point, isn't it? So our total energy total is equal to potential energy plus kinetic energy. Are you with me? So here, you'll find out that since the object is moving with a particular velocity here, you'll find out that our from the relation v squared equals to u squared plus 2as, all right, you found out that our a is equal to, I've done this thing before, a is equals to v squared minus u squared all over 2s. Now I'm going to have that our a is equals to v squared all over 2s because I'm going to remove what do we call it? I'm going to remove our u. Okay, so if that is the case, we are going to be having that our a is equals to v squared all over 2s. So our v squared is equals to 2as, since our u is 0, all right, because it has left from A to point B. So initially it was at rest. So anywhere we see, what do we call it? Anywhere we see u, we put towards 0. So we have that v squared is 2as. Now don't forget that our distance is x. So here we have that our v squared is equals to 2ax. Are you there? So this is our distance, all right? So if this is the case, don't forget that our kinetic energy is equals to half mv squared. Are you with me? Then we'll have that kinetic energy is equals to half m. Anywhere we see v squared, we call it 2ax. Are you with me? That is, we're going to be having 2ax here. So if this is the case, I have that kinetic energy Ke is equal to 2axm multiplying through all over 2. Are you with me? So I'm going to have that kinetic energy is this will cancel this. I have max. Sorry for rearranging the distance. So I'm meant to have my m here so that it will make much more sense. Okay, so our kinetic energy here is max. Are you with me? Then our potential energy here is equals to mgh, where h, where is it? Where h, yeah, is equal to x, isn't it? Yeah, where h is equals to x. Sorry, where h is equals to h minus x. Okay, so we have that mg h minus x. So we're going to be having, opening the bracket, I have mgh minus mgx. So this is my potential energy. So my total energy is equal to potential energy plus kinetic energy, isn't it? My potential energy is equals to mgh minus mgx x, then my kinetic energy is equals to plus mgx. Sorry for using a here. This a is meant to change to g since you are doing under gravity. Okay, so where did I get that? Okay, yeah, it's meant to change to g. Sorry for using that there. So then you have that total energy is equals to mgh minus mgx plus mgx, all right, will give us 0. So I have plus 0. So our total energy here is equals to mgh. So mgh plus 0 will give us mgh. So at point B, you know why we chose, why we use height here, height at B to be h minus x, because we are calculating everything from the earth surface. Am I communicating? So the height of B, of this material, of this body at B, is from here, from C to B. Am I communicating? From C to B. Are you getting my point? So that's why we use h minus x as the value of the height of what, of the body at this point B. So you know, at this initially at point A, we have that total energy is what, mgh, which is what, the potential energy of this body. Then at this point we still find that that the total energy is still what, conserved, which is still what, mgh. So let's check at point C. Now at point C, so now at point C, now at point C. Now, don't forget that, you know, from point B, we will now allow the body to move freely under gravity. Are you with me? So, from B to C. So, automatically, our potential energy here is equal to 0. Are you with me? Yeah, because our height here is already, so we're going to be having mg times 0. Our height is already 0 because we are moving from here to here. So we are going down. We have covered the whole height from, you know, maybe if from here to here is 100, so this is 50 to 0. So our height here is 0. So I'll have that what? My potential energy is now 0. Are you getting my point? So the object is undergoing motion now. So our kinetic energy is equals to half mv squared, isn't it? So have that from the relation that v squared is equals to u squared plus 2as, we'll have that v squared is equal to 0 squared plus 2as. So we have that v squared is equals to 0 squared is what, 0. So I'm going to have 2as. Now don't forget that since it's moving under gravity, our A will turn to G, will becomes what, G. So how that what, V squared is equals to 2G. Then since it's under gravity, okay, since you are considering height now and no more just ordinary distance, our distance here will become from here to here. That is from distance from C to what? From C to A. I get to my point, because all the gravitational pull from here is acting on this object, okay, to this point. So our G will becomes what? H. Are you with me? So it means that anywhere I see V square, I can call it 2GH. Okay, so my kinetic energy is equals to half mv square. So v square, anywhere I see v square, I can put 2gh times 2gh. If this is the case, I'm going to be having that kinetic energy is equals to I'm going to be having that kinetic energy is 1 times m times 2gh. You give me 2 mgh, then divided by 2. Then I have that my kinetic energy is equals to mgh. So my total energy here, energy total, is equals to potential energy plus kinetic energy. So I'm going to be having that potential energy is 0 plus my kinetic energy, which is mgh. So 0 plus mgh you still give me what? Mgh. So if that is the case, we found out that what? At each point, at point A, our energy is mgh. At point B, the total energy is what? Mgh. And at point C, the total energy is mgh. So this has already been able to we've used it to verify that what that mechanical energy is a conservational kind of energy. Okay, so in this energy type, the total energy of the system is always conserved no matter the point at which the object or the body is positioned. Are you with me? So we've been able to achieve this. Okay, we've been able to achieve this and this. So lastly, we are going to be looking at applications of mechanical energy in our daily life, and then we look into calculations under mechanical energy. So I'm not going to waste spend much time on the applications. Under application, we found out that one of the applications is that we use it in driving nail into what do we call it, into wood. Okay, if for instance you want to hit a nail, okay, if this is a nail, you want to hit this nail into a wood. Are you with me? Into a wood. You found out that this is a nail. All right, want to hit into this, you want to nail it into, drive it into this wood. Are you with me? Okay, so you found out that for you to drive the nail into this wood, you will need to raise hammer, maybe from this point to this point. You're going to raise hammer from this point to this point. So if you raise the hammer from this point, okay, to this point, are you with me? You'll find out that you have already given the hammer potential energy, because the hammer has a weight, has mass, right? Okay, and you moved against gravity, that is G, then to a particular height. Are you with me? So at this point, the hammer has already obtained potential energy. Okay, so that potential energy on coming back, okay, the potential energy will be converted back to what? Kinetic energy. Converted to what? Kinetic energy. Initially, when you're raising it, it was potential energy, which I've already explained in the class, in the previous class when I was discussing mechanical energy, right? So the potential energy has been obtained or has been induced to the hammer. Then on hitting it back on the nail head, you find out that the potential energy will be converted into kinetic energy. Then the kinetic energy, which is energy in motion, will now help to drive this nail into the wood. Are you with me? Do you see? This is one of the applications, okay? And another application, this is number one application. Then another application of mechanical energy is in that gun, okay? Is in that gun that uses spring inside, just like I explained before. If you have, for a dart gun to shoot out a material, is not actually bullets, okay? You can load material inside the gun, okay? Now this is the gun, as case may be, okay? Now you found out that if you have this material inside which you want to project, to a particular target, for instance, you found out that when the trigger is being held, if the trigger is being held, the spring will be compressed. Then when the trigger is being released, don't forget that when you hold the trigger, it will compress the spring, and the spring under compression will attain potential energy. We have explained it, okay, when we treated the three types of potential energy: gravitational potential energy, the stretched compressed potential energy, and also we treated electrostatic potential energy, isn't it? So under that stretch compressed spring potential energy, you find out that the potential energy has been induced to the spring. Then automatically, on leaving it, when the potential energy, when the trigger is being released, holding it like this, the spring will be dragged, will be compressed. On releasing it, it will be stretched. Am I communicating? On releasing it, okay, it will be stretched with a what? With a force, with a kinetic energy force, okay. It will be stretched with kinetic energy. That energy will cause the material inside the spring to come out of the gun. Then on moving out, here we have potential energy when it's compressed. Then on leaving, we are going to be having kinetic energy here that will cause the material which serve as as a bullet inside the dart gun. Okay, I said dart gun, which serve as a bullet inside the dart gun to leave and hit a target. So maybe here is a target. Are you with me? So with this, we've been able to treat applications of mechanical energy in our daily life. So we have many ways in which we apply mechanical in anything we do. In lifting up an object, take for instance, as I lift this object, okay, I've been able to, apply mechanical energy today, okay. Even during writing, okay, we apply what? Mechanical energy every day in anything that we do. Okay, let's look at some calculations under this topic. So we're going to be looking at some calculations. Doing some calculations now. Okay, let's solve this calculation. Solution. So a girl is carrying a school bag of mass. So I have mass to be 3 kg on her back and moves 200 meters on a leveled road. So distance S is equal to 200 meter. Distance S or D, okay, is equal to 200 meter. The work done against gravitational force will be, we are given that G is equals to 10 meter per second square. So how will you tackle this problem? The question says we should find work done. Work done is unknown, but we know that work is said to be done when force is moved to a particular distance. So force times distance. Are with me? And we know that force is equals to mg, since we are looking for work done against the gravity. Are you with me? So anywhere I see F, I can put what? Mg. So I have that my work done, the work done by the girl, is equals to mg times d. So our work done here is equals to m is what? Mass, which is what? 3 kg, times G is 10, times D is 200 meters. So I'm going to change any units. Everything is intact. So I'm going to be having 3 times 10 will give me 30 times 200. Okay, this will give me 6,000 joule. So it's in the option, okay, option A. So if you convert to standard form, work done is equals to 6.0 times 10 raised to power 3 joules. So our answer is option A. So let's look at second question.